Hello and welcome to the ReCoDE Perceptions Exemplar. In this presentation I'm going to give you a short overview of the field which looks at images to understand the environment. There'll be some theory and some application. Hopefully this will guide you in the following steps of the practical. There are various different ways in which images can be used in research to measure the environment. For example, looking at socio-demographic statistics, environmental hazards in our urban environments, maximizing production in agriculture, understanding perceptions of the urban environment as perceived by the user, or looking at satellite images to understand commerce. So how do we meaningfully extract information from images? We first need to understand our different types of data. You probably are already well acquainted with structured data. This type of data is typically ordered in rows and columns. Unstructured data, on the other hand, is typically very high dimensional and cannot be ordered in rows and columns. This includes images, text, and audio, for example. Supervised learning tasks already have a label for which to learn the best model for. Unsupervised learning have no output label and therefore are harder to interpret the results. Finally, when we think of models, we understand traditional machine learning models as support vector machines, regressions, k-means, or generative statistical models. Deep learning models, as you may already know, then start to consider very high capacity models which are built upon neural networks. And we'll go into a few examples in a few slides. Before the advent of deep learning, we had traditional computer vision methods. This would typically take an input, extract the features, and then use a traditional machine learning algorithm on structured data to predict the output. Examples of traditional computer vision algorithms include histogram of gradients, or HOG, scale invariant feature transformation, SIFT, or GIST. The underlying principle across all of these methods is to extract small regions of the image and calculate various metrics in order to be able to classify what the image might be containing. Deep learning completely changed this paradigm by removing the feature extraction step. Now we just have the input and we build a model that directly predicts the output. Deep learning networks build more complex representations on top of simpler ones, and we'll show in a few slides how this actually happens. A more recent criticism of deep learning is the explainability. As this method and as these tools proliferate through industry and through our lives, often the question is, why has that model made that choice? As such, there's a huge field of explainable AI which works to build models which do include interpretability from the design stage. And here are two resources which you can read to get a better understanding of explainable AI. So let us begin from the most basic building block of the neural network, the multi-layer perceptron, which has been around now for decades. The principle is inputs come in and are multiplied by weight parameters theta, after which they are summed and a non-linear activation function is applied. This is a single unit, the neuron. As we start to scale by width, there exists a construction of neurons which can approximate any function, and this is known as the universal approximation theorem. In practice, scaling by width might mean that we need infinite number of neurons, which is wholly impractical for our computers. And this is how deep learning has arisen, by trading off width for depth and being able to approximate any function under this universal approximation theorem. So how does the network learn? As the inputs come in, the weights are multiplied, and we get, finally after the nonlinear activation, our output. When we have a label, i.e. under the guise of supervised learning, we then have a reference by which to measure how different was our output from the actual true value. This is known as the error. And if you're familiar with the Newton-Raphson method, it's a very similar concept. We arrive at some value for the error, which can be randomly initialized based on random weights of our network. And our goal is to minimize this loss. So we look at the gradient with respect to the loss of, we look at the gradient of the loss with respect to our weight parameters at this given point. And we want to go in the direction of lowering our gradients. So we update our parameters by taking a step towards this lower value. And this is known as backpropagation. So the loss is, the derivative of the loss is taken with respect to the weight, and the weights are updated. This process continues iteratively until we reach a minimum value, and hopefully we reach a global minimum. So let's tie it all together. We have our neural network activation function. We have our loss, where here we have the mean squared error, which is looking at the derivation from the true value versus the predicted value. And squared penalizes wrong values more than if we didn't have mean squared, but instead mean absolute error, for example. And our goal is to minimize the loss with respect to theta, and we do this via our gradient descent function. As I mentioned, iteratively updating the parameter weights based on the derivative of the loss with respect to the parameters. And here are a few examples of different activation functions. So what happens when we start to think about convolutional neural networks? The convolution is a slightly different operation to what we would call a fully connected neural network. And this works by applying a filter, a sliding filter across the image. And this filter is made up of weights. So these now are parameters. The convolution is actually taken from the field of digital signal processing. And you can see an example of a two-dimensional filter, F being convolved with G. And you can see G slowly sliding across the filter F, and the output is maximized at the place where there is a lot of F in G. Essentially, the filter is quantifying the amount of the signal F in the filter G. ML libraries actually use cross-correlation because there's no need to add an additional operation to flip the signal. So when we start to stack convolutional filters on top of one another to build a neural network, what we have is multiple feature maps. So we don't need to just have one filter. We can have numerous filters stacked after one another, and this will allow us to look at different features. For example, what if we wanted to detect diagonal, horizontal, or vertical patterns in the image? As we go deeper into the CNN, the deeper layers process the feature maps of the previous layer, and we start to build those more complex representations, as shown in the illustration on the right. In addition, what we have is that the shared weights of a given filter across the image actually minimize the parameters, the total number of parameters in the network, and allow for neural network training. CNNs have existed well before the past decade. We have an example of LeNet on the left-hand side and AlexNet, which was invented in 2012. There are differences in the neural network architecture, but those differences weren't the reason why CNNs revolutionized machine learning as we know it. What really lit the fire was the creation of ImageNet by Fei-Fei Li, a huge image database with labels that was used to train these neural network models on. In addition, GPUs were invented around 1999, and this allowed for rapid processing of parallel operations. As such, we see a substantial improvement in classification error for image classification challenges with the advent of AlexNet. Here are an example of some of the architectures which have revolutionized CNNs in the past few decades. So previously, as I mentioned, LeNet we see that there are only 60,000 trainable parameters. AlexNet blew this out of the water by having 61 million trainable parameters, which, as mentioned previously, was possible due to the huge number of images it was trained on and the GPUs which were able to speed up processing. VGG did not hold back and has scaled to more than double the number of parameters. The Inception net or Google net actually was able to scale back by including new components, and in addition so was ResNet by including residual blocks. Within machine learning and computer vision specifically, we're not always interested in just classifying the image. We might also want to detect objects and bounding boxes within the image, look at instance segmentation pixel-wise, or completely segment the entire image. In addition, for classification, we might be interested in looking at urban environments which are associated with wealth or with poverty. We might be interested in understanding environmental hazards and traffic management, for example. We might be interested in extracting footprints of buildings and looking at neighborhood change within given cities, or understanding the entire landscape of a street view. Object detection networks are largely split up into two different types. We've got the two-stage detectors and the one-stage detectors. The two-stage detectors have been iterated upon to arrive at the faster RTNN, which uses a convolutional neural network to extract a feature map, after which region proposals are thrown out onto the image and then a separate classifier is built to predict the object detections. Faster RCNN has much higher accuracy than our one-stage detectors. However, the trade-off we have is time. For the one-stage detectors such as YOLO, the entire process is done in one stage, hence the name. The image above is from a separate project from Pathways to Healthy Equitable Cities, and it shows some features that have been extracted such as umbrella, car, truck, bus, and person. Semantic segmentation's goal is to label each pixel based on what class it belongs to. So in this image we can see car, tree, building, or sidewalk. You might notice this, you might find this architecture a little bit familiar. It's based on an autoencoder, and what it uses is a convolutional neural network to encode the image and a transposed convolutional neural network to decode the image to learn the entire feature map, to learn the one-to-one correspondence from the input pixels to the output pixels. So we've looked at how some of these images are being used. We've looked at feature extractions from old to new. I would recommend the Coursera Andrew Ng's course, as well as Jeff Hinton's course, as well as reading, if not the whole book, some chapters of the Deep Learning book by Inga Yoshua Bengio, and one more author who I've forgotten. In addition, the tutorials from the Deep Learning Indaba have been very helpful for myself. For object detection and semantic segmentation, I'd recommend the TensorFlow Deep Lab API, which we'll get a chance of having a hands-on go with in the final stage of this ReCoDE exemplar.